Welcome to the electron configuration lesson. In the electron configuration, its point is that you're looking at where electrons are in, whether that is an orbital or a different sublevel. So each sublevel, as noted, so you have a S sublevel, you have a P, D sublevel, and you have an F sublevel. So these are your four sublevels. And so these are your sublevels. And so in these sublevels, you have a bunch of orbitals. And so in the S sublevel, you only have one orbital. And so each orbital, let's just note that each orbital contains up to 2 electrons. So, if you're going to contain up to 2 electrons, that means that S sublevel has 2 electrons. And if we go to the P sublevel, we have 3 orbitals, and we have 6 electrons. When we go to the D sublevel, we have 5 orbitals, and that will result in 10 electrons. And in the F sublevel, we have 7 orbitals, and then we have 14 electrons. So this is sort of the basis or the foundation for electron configuration. And so let's take steps to build on to continue. So this would be the orbital diagrams. So in each orbital diagram, you need to have an up and a down. And these arrows are known as electrons. These arrows are symbolizing electrons, and you always start from the lowest energy to the higher energy shells. So that would be the Faber's principle, in which you start from a 1s and you lead up to 1s2, 2s2, 2p6. So you're going up in energy shells. And so the other rule is that you need to have one up, one down. This is the Pauli exclusion principle. Whoa, I can't spell principle. Principle. So in the principle, you are opposite spinning electrons. There are opposite spinning electrons. So those are already 2 of the 3 rules that are knocked out. So let's try an example. Let's say we want to find the orbital diagram of oxygen. So we always start with 1s2. So 1s, there's going to be 2 electrons in the S sublevel, and we have 1 orbital. So in the second S sublevel, we also have 1 orbital, which consists of 2 electrons. So now we have 4 electrons so far. Since oxygen has 8 electrons, we need to try and get to 8. So let's see if we can. So now we have 2, and P sublevel has 3 orbitals, and you represent these orbitals with these different lines. And so now you can go, now is where it gets tricky. If you were to go like this would be basically incorrect because you can't leave off a orbital. And so this is where something known as Hund's rule comes in. So Hund's rule states that all orbitals have to have at least something down before you fill them up. So in this case, if we go back in time, we need to fill all of these up. We need to fill all these orbitals up, and then we can go back down. So that means we already have 8 electrons. So this is done. We know that we see there are 2 lone pairs that don't have a pair. And we also see that the valence electrons, we have many valence electrons. We have 2, 4, 6. How do I know I have 6 valence based on this diagram? It's simply from the fact that it's the highest level of energy. So I have 2. That's going to be my highest level of energy. So if I had 1s2, 2s2, 2p6, but since oxygen only has 4 in the p sublevel, I can count my highest. My highest is 2. 2 plus 4 is 6, so that's 6 valence. So that's like the introduction to energy and this idea of electron configuration. So then let's try a different example, something more complex. Let's try Mg. How would you get to Mg? Mg has 12 electrons. It's the same process. So up, down, you get to 2. Up, down. So now you're at 4 electrons. And now you're at the p sublevel. But you're still in the second level. So fill up all of them first just to build a good habit, even though you don't necessarily need to do that because you're not at enough. You only have 2, 4, 6, 8, 10, and now you need to go to the third level, which is 3. That's 1 and 2. So it's perfectly at 12 electrons. And so you can see that based upon this diagram, you can tell that there's only 2 valence electrons. And that's simply because it's already at the highest. So if we were to write this in electron configuration, we would do 1s2, 2s2, 2p6, 3s2. And so in this highest level, there's only 2. There's only going to be 2 valence. And you can even check on the periodic table, since magnesium is an alkali earth metal, it has 2 valence. So it's 2 valence electrons. It's in the alkali earth metals, so it's 2 valence. So many ways to check the valence electrons, though you can use the strategy. Let's try one more example. And then this time we'll do chlorine. So how would we do chlorine? Let's go 1s, we have 2 electrons, and the 2s, we have 2 electrons. 2p6, we have 3 we have the sublevel with p that has 3 orbitals. So 2, 4, 6. And then now we're back to 3. 1, 2. So now we're at 4, 6, 8, 10, 12. We're at where magnesium was, and then we have to continue. So that's 3s. And then we are now at 3p. So we're at 12 so far. We need to get to 17. So 13, 14, 15, 16, 17. So now that we're at 17 electrons, we can stop. So we have one of these that are lone. So we also have 2, 4, 6, 7 valence electrons. With 7 valence electrons. And we can also write it as an electron configuration. So it is 1s2, 2s2, 2p6, 3s2, 3p5. And so that would be the same thing as chlorine. So I hope this video has helped you, and I'll see you in the next one.